Hello again, this is Desmond Aubrey from Rarefied Technologies Southeast Asia, or known as RareTechSEA, and we're on part 2 now of Modular Shell-and-Tube Heat-Exchanger technology. And during the last, we ended off talking about the novel technologies involved in this special design. I call it the Gasalta style designs. All right, it's unique, and they were actually was covered by 3 patents which have long since expired. But the ideas were novel, and he patented them around the world, and so he covered himself. And as I say, that technology was then brought into South Africa, where it actually made very, very good progress. Effectively, Brazil is where he did a lot of his work, and also parts of South America, Panama, and so on. I think he eventually settled in Panama, and also South Africa did very well. So we had these elastomeric tube seals, vented headers, single headers, which I'll explain in more detail later, modular construction, where we can actually clip them together. Standard components, beauty. Sitting on the shelf, you get a call from a client, an inquiry, you have a look at it, yeah, we can put it together. How soon can you deliver? Oh, 3 days, 4 days. What? For a purpose-built unit within a few days, it's very good. And then we spoke about the U5, which is the bigger unit that we typically use for the chemical industry, and U3s, which were more like the oil coolers, they're low-cost type stuff. And then we also spoke about tank systems. Now we move on to the next slide, and let's see what we have to say there, if it does what it's supposed to do. All right, let me go back, sorry, it shot ahead. So here we'll start to talk about the historic market analysis of these products, let's say in South Africa and Southern Africa. Around 38 years actually of accumulated experience in South Africa and Southern Africa, as in Zimbabwe, right up into Africa. They were exported up right high in Africa, and also to some of the other islands around us. At that point, over 3,300 projects, which is a lot. Over 100 clients at one stage, and over 50 international projects where people had bought for particular projects because they knew the technology. And then the 2 scenarios that I cover here in the historic marketing analysis is using a mining basis. In other words, if mining was your basic income source, or if you're just looking at manufacturing, we exclude the mining. Mining was very profitable actually at one stage, so they did very well out of this. The 2 older guys that owned the business did very well. I suspect they retired very well. So let's go on to market mining basis. So what we've done here is to look at the different aspects to the market. So petrochem, air-based, steam and condensate, oil-based, elution systems, water-based, okay, relative volume. But when you talk about profitability as to what makes the most money, you'll find that the elution systems made a lot, because the payback for the mine was very quick. They pay these things off in virtually no time. So it became a really big part of the business. And these units are still running in South Africa many, many, many years later. So they actually found a right home. What the mines typically would do, they'd run 2 or 3 that have of a particular unit. So they would have one running, one on standby in case there was a problem with foul up or something else on the units, and then you have another unit going in for refurbishment. So if you needed to get stuff, new seals put in and so on. Because truthfully, the miners were not that good at maintaining. And so they would just pass the thing back to the factory and say, please, can you guys maintain it for us? And so we'd have a contract to maintain. It was actually very profitable. And then let's take out the mining part of it, and let's just look, for instance, for manufacturing industry. So we have petrochem, air-based, steam and condensate, oil-based, a big portion of it, you see, if you exclude the mining, and water-based cooling. So that water and oil was a big part of the business. And then steam and condensate here, which is a real typical application. This was most of your business. And it's nice business, easy business. And then profitability index, again, petrochem, you can charge a lot more because it's complex, and their standards are quite high. The specifications they work to can be a little bit onerous. So you're really going to take a lot of care, a lot of inspection time and everything involved. Whereas The rest of the industry is pretty straightforward. You've got your water-based, oil-based, and steam and condensate. That's more than half of your profitability. So you can focus quite nicely on this part of the market as a startup when you get going. Once you've really, you're comfortable, he talks here about air-based, but that's basically air coolers and so on, which for compressors, quite an interesting application. And we'll see a few of the pictures later of this. You wouldn't think so, but it is. So basically, you can literally say from there to there is where you're going to make your profit. This petrochem sounds nice, but it's not hassle-free. It's got a little downside to it. Very demanding. Then we move on. Let's talk now about the spiral shell side baffle. This is really novel, and one of the patents that Gestalt had was for this kind of design. Okay. So you can create optimized heat transfer. What actually happens is the baffle itself is made out of segments, pressed segments. Today you can water jet or you can laser cut. And then they're joined by pins. There are different types of pins as well. And they within different lengths. These pins we call HS spacers. And they can be in different lengths. So the bundle's spiral pitch can be adjusted and modified to suit the application that you're working with. It's very interesting. It handles fouling very well, actually. So you can go, I think our biggest space is 120 between each segment, so for one full spiral, we're talking about 720 millimeters because there's 6 segments, yeah? What we do, I'll talk about the ranges here. Low fouling, it actually, really, with these kind of fluids, I was very surprised with very high dust content or particle content, rock content really. You had very little fouling, all right? Easy to clean. So there's reasons for that. You actually can pop the headers off actually and slide everything out, slide the whole bundle out and just water blast it, give it a good clean and put it back in again and just seal up again. All kinds of things. You can also clean it from the outside. You don't have to have CRP or anything to work with these. Very simple. Designer control. What's nice for a designer is we've got the way you do the design. I'll talk you through now once I've talked about this. Is that you have a very large pitch down to a small pitch. You can have 120 spacer right down to I think our smallest is 2.5. All right. So you can have constant pitch bundles. Typically, when you've got single phase fluids, you have a constant pitch bundle. But you can have variable pitch. So for instance, if you've got a condensing fluid, what we do is we step through the length of that shell. You might step down in 3 graduations. So you start off quite big where it's vapor. And as it starts to condense, of course, the density specific volume is very different for a vapor versus condensate. And then by the time you get to the end, now it's effectively all liquid if you're fully condensed. So we then cram up the spacing. So we have what we call a variable pitch. So if it's a condensing fluid, you're going to reduce. You're going to go big to small. If it's expanding or you're vaporizing, you're going to come in as liquid and come out as vapor. So we can actually then go smaller to bigger, which is neat. All in this actual bundle. So the way we work a design is what I term the inside-out approach. When we start to get to the modular designs, I'll put a bit more detail into this. But we start with the tube side, and we basically modulate on velocity in the tubes. We don't want to go too slowly, otherwise we get fouling. And you don't want to go too fast, because you then start to get erosion. And above a certain, one, the pressure drop gets very high, but two, the erosion. If there's any dust or any particles coming through, you can kind of basically erode right through the tubes. So you've really got to manage yourself within a certain band. And we used to control carefully on that. So you would do the tube side. That would determine how many modules need to be in parallel. And then you would go and you'd work out on the shell side to get the shell side optimized at the right flow rate and velocity and pressure drop. And then from that, it would determine how long your exchanges needed to be. And if they were over a certain length, what you would do is you'd wrap it around and then wrap it again. So you'd end up with a multi-module system. And that was the design process, very straightforward. And you can always go back as a designer. You go through step by step by step, and you go back and see if you can tweak it a bit better. All right, so it's basically the inside-out design method. It works very well. But a lot of people who design these things, shell and tubes, don't even think about all these things. And then they end up with huge mismatches between the tube side and the shell side. The one dominates the other, whereas in this case, nothing dominates anything. All right. So talking through the elastomeric seals, the seals that we use, you'll see that they're essentially round, and you've got round cutouts inside, and then basically the tubes pass through here, and this part here seals against either the header, typically the header, or part of the shell. But what happens is, as you put a pressure on this thing, it squeezes, and it actually squeezes onto the actual tube itself and squeezes out onto the shell. So the kind of elastomers that we play with, things like EPDM, which is kind of the standard chemical one for most applications. Nitrile we used for oils, so they didn't run into trouble. Vitons, yeah, for chemical application. Silicon for more high temperature. Was quite useful. We had a red seal for that. Chloroplene as well, and then you had special versions of some of these seals. But things like calories and all that are very, very expensive. So we would go away from that. And what we would do is actually put a shield, a heat shield, on either side of the seal. And then so it's a heat shield or a chemical shield. We would actually keep the nasty stuff either with hot fluid or in other cases the aggressive chemical. Keep it off the seal face. And that seemed to help us very well. And so we were actually able to get up to pretty high temperatures for an elastomeric unit, which is not bad at all. When the first units came out into South Africa, apparently they hadn't sorted out this is before my time, all the heat shield technology. And then what would happen if you had the wrong seal arrangement under high temperature? They start to extrude, they squeeze. So by managing carefully and also stiffening your seals up a little bit and so on, we learned how to manage that problem. Very trick technology. Okay. And then let's talk about these vented headers. So what we've got here is we've got these individual headers. This is going to be a tube side header, and that's going to be a shell side header. Then we have certain seals that are in here, seals there, and then we have two plates, pressure plates, and we then have seals on the other side, another pressure plate. And then we have also pressure transfer mechanisms, which kind of keep everything going nicely together. And then we bolt it up here at the ends. We've got an end cap over here and different types of end caps. This is actually a cast end cap, which is cheaper really, but you've got to watch out for porosity, or manufactured end caps. That's a manufactured end cap, for instance. Okay, this is the original casting style, and you'll actually see here this should be put downwards. It's actually for a drain. If you wanted to install, you actually drill and tap and put in a drain if you want to. So there's a lot of tricks that you can do with this technology. And then also at the end they put a hole, also helps you to pull it off, but also we put a thing there telling us how a warning plate just to remind us that we mustn't over talk. You talk up to a certain point, and that's it. Don't overdo it with elastomeric seals. All right, so we have this concept of individual headers. These are the head. That's a header, that's a header. Fail-safe atmospheric gap, so if there's a leak, it's going to come out the gap, which is a pretty good idea, all right? Double elastomeric seals, of course, there's extra seals involved here to do this. This was the standard design that we did. Very good for petrochem. No cross-contamination between the two fluids. We couldn't mix things up. We couldn't get stuff coming in and squirting back into the shell side. We kept them plain. And free-floating tubes. The tubes actually, I'll show you another picture later. The actual tube sitting in the seal, go back to the previous one. When they sit in the seal here, they can free float. So when you build it up, your tubes are not compressed, okay, which means the tube life is a bit better. And then replacing individual tubes. Actually, I'll go back a slide. When you strip the unit down and you get to this point, you could literally slide a tube out completely while the bundle's sitting in the inside the shell, and you pull the tube right out, and then you slide another tube in. Okay, you can't do that with normal shell and tube exchangers, because those are normally either welded in or back expanded, or a combination, and big problem to change tubes. Whereas these, it's very easy to change tubes. All right. So there's a lot of tricks to this technology, and so you'll see how we expand this from a single module into multi-modules, where it gets quite complex actually. And then we talk about single headers. This was introduced later, actually after my time, after my original time. As a single header to bring the costs down, what we do is there's a combination set of plates inside here, but you have less seals. And so you can have your single header. What you'll see here, there's no, for instance, a single header, you can have the entrance socket on the header itself passing in for the tube side. The shell side, you then weld it straight onto the shell, so it comes through and across, all right? Or you can actually have the entrance in the end cap. So you have an end cap with an entrance coming straight in, which is quite nice, better for the flow anyway, coming straight in, and then it'll face the tubes and off you go. So that is another alternative, which was quite a nice development. So single header, single elastomeric seals, you save on seals, you save on pressure plates. It's quite cost effective. It's a bit cheaper actually. Free floating tubes as normal, and again you can replace individual tubes, so very easy to go and replace them. So if you've got an oil cooler or something and you're wanting to work on it, you just pop the ends off, leave these studs in place. You see it's got nuts both sides, and then you pop it apart, and it all, just like a Meccano set, you know, it all falls out, and then you can actually work on them, clean it all up, and then put it back together again. So it actually extends its life. You know, these units can last a long time. So that's the concept of single header. And then the kind of idea of the standard components, you get all kinds of things. This is what allows you to connect three modules in parallel. We call it a three-way straight. So straight because it comes in and then passes through to the next, and you might get a three-way 90 where you come in on one of these. So far I haven't seen them go center, but typically one of the ends. So you can come in at 90 degrees here if you like. This is a two-way 90. Okay, single header. This is a 3D drawing of a spiral baffle arrangement. You'll see how there's 6 segments to get a full spiral, and these are the HS spaces that join them up. And then you build this long bundle, you know, the actual shell side by itself, the cage, and then later you slide the tubes in until you build the actual bundle, and then you slide that into the shell. And there's different types of plates, like you'll see this one is straight through. This one's got little retainers at the end to prevent the tubes ever sliding out, you know, because they might slide a bit on the rubbers originally when you're setting it up or you're nipping it up, it stops them sliding out. And then here you've got spaces to give you the air gap that we spoke about when we spoke about air gaps here, there. The way we do that is we've actually got extensions on the actual tube sheets. Then you've got the elastomeric seals, you've got this actually goes onto the actual shell. Then we've got other things like we call Mobius springs. They're special springs that we actually can use to take up much higher temperatures. So they give some flexibility and it doesn't overload the seals. And can go back and show you where you will see that. You'll see it on here in this arrangement. Inside here there are these spring discs, and we have a special manufactured end cap, and then what happens is this plate here then presses on these springs. You have what we call an SP1 or SP2, 1 spring or 2 springs. So that talks about these guys. And then you've got the end caps. This is a cast end cap. Casting has its own issues, you know, to get integrity of the casting, but they're quite cheap generally. And then you've got manufactured end caps. Again, this is another end cap, but it's got space on it to allow you to put springs on it. And just a stand. This was a concept that came in some of the early designs. You don't see it too much later. They call them S plates, where you actually can force the flow backwards and forwards inside the tube bundle. So you typically, most big heat exchangers would have had, you know, they're forced because of the mismatch between fluid velocities and shell side. They have to have multi-pass. But what we found is S plates, in the beginning they played with them, but it's not really worth the effort very often. If it's a case like that, for most of our bigger applications, you should never use that, only for very small applications. What did I also, there was something else while I was talking about. The interesting thing about manufacturing is when I came back to the business and took over, when I first got there, they were doing everything still the old way, you know, machining by hand. And they'd have lathes and they'd get on with it and drilling machines, and the tools had got old, you know, and so there was a lot of wobble in the tubes, and so the accuracy wasn't very good. And so eventually we went over to a more modern system, CAD-CAM. And we could, build stuff, beautiful tolerances by using computer-aided manufacturing. And so, especially for these kind of plates, and I remember with the guy that was doing the assembly, I didn't tell him that we were tightening tolerances. And I would say to him, "How are we doing?" And he says, "No, these are perfect, smooth, and they go on easy." And so, I eventually was able to tighten the tolerances so we get better sealing and better efficiency, and so on by using computer-aided manufacturing. And they were beautiful. They would come out with really. So all of this, in the old days, you used to have to put punch pins in here, you see. And what they did on some of the designs is they wouldn't put these center pins in, and then you get a bit of a bow in the plate. Not a big deal, but you get a bit of a bow. That elastomeric tools take it up. But when you go to cam, you can actually put in these dimples, these protrusions, the spaces that you need, and you actually get a better distribution across that face, a bit of pressure distribution, force distribution. So that's a little bit there, and then let's see if we hit the next one, and then I might stop. So just at this point, just to give the idea of modular construction, what's happening is you're actually taking these single modules, that one plus that one plus that one, and you're lacing them together. So you can, if you think about it, this is one at the bottom, that's another one there, and that's another one there. But what you then do is you join them using, this one's actually got a turnaround header. So you'd come in here, you'd go along, get to the end, and then you'd have one of these turnarounds like this. I'll show you something like that, but without this. So just with that and that, we call it a turnaround header. And so that lets the flow come down, and then it goes along, another turnaround there, come out and exit. So you'd have inlets and exits. And remembering when you do multi-module, you must go with counterflow. If you go with parallel flow, you're going to end up with very, very poor heat transfer. So everything's aimed to be counterflow. Now, of course, you can have condensate, so you can have steam coming in, for instance, and steam on the shell side and steam on the shell side come out as condensate. Normally, we are much smaller exit, actually, for condensates. And then you might have the process fluid coming in, but in opposite directions. And this one, you won't see, it's on the other side. And then the process fluid would go out and up and out there. So we can actually play with different header types. You can have a header that looks like this, and you can then point it, up or sideways or down or whatever you like. So there's so much flexibility when we start to work with this multi-module system, and you'll see some very big units later. Now this particular one's obviously a little bit higher temperature because of the steam, so they've actually got probably an SP2 in here. So you've got two springs in here, you've then got the end cap, and then you tighten it all up. And then what they do at the end is they put a little washer there to say, hey, don't over tighten. Red, So when you first get these units into position, your maintenance needs to go around and just check its torque. So you will then do a cross tightening sequence, there, and just watch your torques, and then don't go greater than that. Just stay within the torque range. And if it seals, that's it. Don't push any harder. Not necessary. Okay. So there's a bit of an art to them. The stands on these in the old days, I thought they were very flimsy, and you'll see later. When I took over, we got very rigid and robust. I didn't like these stands, to be totally honest with you, because you want to give support. The people go and lift these things into place, and if you're not getting a lot of lateral support here at all. And these long studs, I was always worried about denting shells and so on. So you'll see as well, there's also different types of spaces that they have, shell spaces. These are fabricated. You've got a curve on there, and a piece in between. Okay. There were others in the beginning, also made out of wood for certain insulation. You can do them out of wood too. It also works. But later, I also then put lateral supports in and then built it up, so it made a very solid frame. Because these frames were not very nice, and if they weren't looked after very well, they could come loose. But again, that was a development done in South Africa. Later, I pushed it to be a lot more let's say complicated, but strong, very strong, especially for the mining applications. But you can see it's very easy to put something like this together. We would have certain standard shell lengths, and then we would have tubes, and typically, your tube would arrive at something like just over 6 meters, and we chop 6.1, and then we chop them in half, and you'd end up with 2-3 meter modules, for instance, that kind of thing. It would save, you would actually optimize your materials, so we didn't have very high wastage. And we could do the same with the shells, because ours used to come at 6 meters typically, and you cut them in half, But if you want shorter units, in this case it makes no sense to go shorter. What this unit actually is, if you think about it, it's one unit, same unit, same unit. So it's effectively 3 times the length of that is the contact length of the thermal length of your fluid, okay? This allows for very, very efficient energy recovery. Far more efficient than most plate exchangers. Most plate exchangers get a bit mixed up sometimes between what's happening on the one side and they're governed on the other side. Whereas with these, we can control the tube side. You know, you can put a flow in, okay, it'll be within the right range. It's one pass in series, and then we add until we get the full thermal area that we require. And then we can also play tunes on the shell baffles until we shorten and compact the whole unit. Not so easy to do in plates, not so easy, but with this kind of arrangement it's very easy. So what I think I'll do, I'll stop there. We've gone long enough for now on part 2, and then I'll pick up on part 3 and talk through a little bit more for you. I hope it makes sense. I haven't bored you. Okay, thanks for now.